Welcome to the Data Communication Masterclass, focusing on signals and data transmission. Our focus will be on analog and digital signals and baseband transmission. For information to move in modern communication systems, it must travel efficiently from a sender to a receiver. Raw data cannot travel directly. It must be converted into physical, electromagnetic signals. The success of communication depends on how well the signal carries information without loss. A signal is the physical representation of data as a function of time and space. Examples include electrical signals, light pulses in fiber optics, and radio waves. On the left, you can see graphical representations of analog and digital signals. We have two main types of signals: analog and digital. Analog signals are continuous and represent physical measurements. Digital signals are discrete and are used for computational processing. Analog signals are continuous in both time and amplitude, varying smoothly over a range. They typically form a smooth waveform, like a sine wave, and have an infinite number of values. Examples include human voice and temperature data. Digital signals carry data in discrete steps, optimized for computers and electronics. They utilize discrete values, such as 0 and 1, forming a step-like waveform. Mobile and PC data are common examples of digital signals. Comparing analog and digital signals, analog signals use a continuous waveform, while digital signals use discrete steps. Analog signals are easily distorted by noise, while digital signals are more resistant. Analog has an infinite range of values. Digital has limited levels of 0 and 1. Analog is used in technologies like radio, while digital is used in laptops and smartphones. Signal integrity is determined by how signals react to noise. Analog signals are easily affected. Small noise changes the amplitude significantly. Digital signals are highly resistant because threshold levels keep the 0 and 1 states distinct. Signal conversion is vital for modern communication. Analog to digital converters translate real-world data into computer bits. Digital to analog converters translate bits back into audible sound or visible light. These conversions are essential for streaming and digital broadcasting. A periodic signal completes a pattern within a fixed time frame, called a period, and repeats that pattern over time. Because they repeat, periodic signals are mathematically predictable and can be defined by the equation x of t equals x of t plus t. Non-periodic signals have a random nature, changing constantly without repeating a specific pattern. They represent real information like human speech and data streams, and are unpredictable because they cannot be defined by a simple repeating formula. In summary, periodic signals are predictable, have a mathematical model, and are simple waveforms. Non-periodic signals are random, represent real information, and have a continuous frequency spectrum. The cycle is the fundamental unit of signal analysis, representing one complete pattern of a signal. Understanding cycles is vital for calculating frequency and periodicity in signal analysis. Periodic analog signals are categorized as simple or composite. A simple signal is a single sine wave that cannot be decomposed. A composite signal is made of multiple sine waves with different frequencies and phases. Most real-world communication relies on composite signals. The sine wave is the fundamental unit, the most basic analog signal, and the core of Fourier analysis. It cannot be broken down further, acting as the mathematical atom of the signal world. Let's explore the parameters of a sine wave. These include amplitude, which is the maximum height, frequency, measured in cycles per second, and phase, which is the relative position in time. Amplitude indicates the strength of the signal, representing the peak value. High amplitude means a strong signal, such as loud sound or bright light. Low amplitude means a weak signal, like faint sound or dim light. Frequency is the number of cycles completed in 1 second, measured in hertz or Hz. For example, 1 kilohertz is 1,000 cycles per second, and 1 megahertz is 1 million cycles per second. Period, denoted as quote, is the time required to complete one single cycle, measured in seconds. It is inversely related to frequency, meaning as frequency increases, the period decreases. The formula is F equals 1/T. There is an inverse relationship between frequency and period. High frequency corresponds to a small period, resulting in a, quote, compact waveform. Low frequency corresponds to a large period, creating a, quote, stretched waveform. Phase describes the wave's position relative to time zero, measured in degrees or radians. Phase shifts are critical in modulation techniques such as phase shift keying, or PSK. Real communication signals are composite signals, composed of many sine waves combined. This complexity is necessary to carry actual data patterns and voice nuances effectively. Fourier analysis, a foundational concept, states that any signal, regardless of its complexity, is the sum of various sine waves. These sine waves vary in frequency, amplitude, and phase. A periodic composite signal produces a discrete frequency spectrum. The component frequencies are discrete multiples of a fundamental frequency, such as f, 2f, 3f, and so on. A non-periodic composite signal produces a continuous frequency spectrum. It contains an infinite range of frequencies within a boundary. This type of signal is common in data transmission, where bit sequences are non-repeating. Bandwidth is the range of frequencies present in a composite signal. It is calculated as the difference between the highest and lowest frequencies present in the signal. Bandwidth consumption is related to the data content. For instance, a TV signal requires high MHz bandwidth to carry rich video and audio data. The rule is simple. The more data you send per second, the more bandwidth you need. In digital representation, binary ones, 1, are represented by a high voltage level. Binary zeros, 0, are represented by a low or 0 voltage level. The image on the left shows this representation. Bit rate is the number of bits transmitted per second, and its unit is bits per second, or BPS. Larger units include kbps, mbps, and gbps, representing thousands, millions, and billions of bits per second, respectively. Bit length is the physical distance occupied by one single bit in the transmission medium. It is analogous to, quote, wavelength in analog signals and is calculated as the speed of propagation divided by the bit rate. There is an inverse relationship between the bit rate and bit length. A high bit rate means a small bit length, where bits are packed closer together. A low bit rate means a large bit length, where bits are spread further apart. According to Fourier analysis, a digital square wave is actually a combination of an infinite number of sine waves. It is composed of a fundamental frequency, designated as f, and its harmonics. A digital signal is primarily composed of the fundamental frequency and its odd harmonics, such as f, 3f, 5f, 7f, and so on. Even harmonics have 0 amplitude and are not typically present. Limited bandwidth causes signal distortion because high-frequency components are cut off, making the digital pulse's sharp edges round off. A wide bandwidth allows more frequencies, resulting in a sharper and better signal. The time domain plot shows how the signal's amplitude changes relative to time. It provides a view of the waveform shape, such as sine or square, which is the pattern of the signal over time. The frequency domain plot shows the strength of each frequency component present in the signal. It reveals the necessary frequency components and the bandwidth required for the signal. Digital signal transmission is the process of sending discrete zeros and ones through a medium. It ensures the binary information remains intact from the source to the destination. Baseband transmission is the direct transmission of digital signals as pulses without any modulation. It is fast for short-range local networks, offering direct delivery. Baseband uses the entire bandwidth for a single transmission, meaning only one signal can travel at a time. It is cost-effective due to simple electronics and low deployment costs. In summary, signals are physical representations of data. Digital signals are noise-resistant. Bandwidth dictates data capacity, and baseband offers a simple path for digital bits.